Okay, hi again. So now we go continue part 5, okay, of this chapter. Right. So previously we have learned on how to, to derive a rate law for each of the three important steps in the mechanism, which is adsorption, surface reaction, desorption. But I stopped at the surface reaction step. So as for in your textbook, okay, the surface reaction, okay, the surface reaction step can be described as either following the single site. Okay, I've already explained on the part of, wait, this is single site for surface reaction model. All right, so A dot S, B dot S. And I also have touched a bit on the dual site. Okay, so example of a dual site is something like this. Okay, so let's have a look. Okay, if it's a dual site, okay, so for instance, okay, A dot S plus S, B dot S plus S. So one could be something like this because it only involves A and B. Okay, but if let's say if it involve, two reactants and four and also two product, okay, it can also be a dual site. Okay, so for this kind of reaction, it will be the rate law will be Rs equals to Ks Ca dot S. Okay, since A is attached on S, that's why we call it C, and then Cb dot S. Okay, similar goes for CC dot S, CD dot S, and over capital KS. And again, capital KS is actually equals to KS over small ks over small k minus S. Okay. And then it also could be for that dual side, it also can be attached like this. Okay. So I hope that you can read by your own. Okay, so another mechanism how surface reaction can be described as, the third one is being described by Ellie Riedel. So how is Ellie Riedel mechanism? Okay, for example, let's say you have reactant A and B, and then you produce a product C. So it will be something like this. Okay. In this case, in early radial, okay, B will not attach on the active site. Okay, so you will see that B is actually attaching, attaching with A. All right. So only A that attach on the active site. So it becomes A dot S plus B. So B is normally gas phase and then produce C dot S. Okay, so how we'll create or how we derive the rate law, it will be RSKS. Okay, since A is attached on S, so CA dot S. B is not attaching on the active site, so that's why it remains times PB. Okay, so this is the difference lah. Alright, and then we have product C dot S, so that's why C dot S over KS. So this type of mechanism, what we call it, Ellie Riedel mechanism. So this is only in a surface reaction. Okay, so the after, okay, we have gone through adsorption, surface reaction. Now we go to the fifth step, which is desorption. Okay, so for this part, it is desorption. Okay, so actually desorption is like similar to the adsorption, but it's opposite signage. Okay, so for instance, in this case, you have already produced IS, so it's continuous. So you look, it should be a continuation. So N dot S. So here we start with N dot S. React to produce I dot S. So after you produce I dot S, then it will be desorption. So I dot S. So you will desorb the product I from the catalyst surface. So this is how we derive the rate law. KDD stands for the desorptions. Okay, so CI dot S because I is attaching on S. So here is pi. Why is pi? Because I pentene is in it's not attaching on any of the catalyst side, so it's a gas phase. So it depends. If it state there gas phase, then you put P. But if it's not a gas phase, then you put C lah. And then times CV, because S is come back to the vacant side. Over is actually KD lah. Okay. KD meaning capital K, D is desorption constant. But you can also describe KD as KI, where KI, okay, if you refer to the textbook, okay, where is, you refer, later you refer to textbook, you refer to the desorption part, where KI is actually 1 over KD, okay. So this is like a friendlier, friendlier version compared to this version lah. Okay, but either one, you can use either one. Right. So let's look in your textbook. So I think desorption is like similar things to the adsorption. So C dot S, okay, C plus S. So you describe. So here C is carbon. Carbon is as a gas, so that's why P. Okay. So KDC is actually desorption equivalent constant for carbon. Okay. All right. So now let's go to the, okay. If you follow the mechanism earlier that that we have go to the previous part, okay. If you go here, okay, you will see how to synthesize a rate law. First, you select mechanism. So we have selected already the first, the mechanism, which mechanism for adsorption, for surface reaction and desorption. So for every step, you need to produce the rate law. Okay, now we go to the second part, which is assume a rate limiting step. Okay, so let's go to the rate limiting step. Right. So among these three, okay, among this adsorption, surface reaction, and desorption, which one is the limiting step? Again, you need to understand back what is limiting step. Okay, limiting step is the part is the slowest step. Okay, so this limiting step is very important to determine the overall rate of reaction. Okay, so in this chapter we assume that, okay, if in chapter 1 we assume that surface reaction is the slowest step, so that's why we will choose this reaction rate to be the overall rate, reaction rate for this reaction, instead of you choose RAD or RD. So we choose this RS because it is the slowest step. Okay, so this is step 2. That's why we choose RS here. And then what happened to this rate law, the rate law for adsorption and desorption? Okay, so we are going to use this rate law, okay, to determine our unknown value. Okay, so since we will be using this RS as our overall rate of reaction, we need to know what is Cn dot S, Ci dot S. We need to, to produce a rate law that is meaningful. So N dot S is actually, we read as the concentration of N-pentene that adsorb on the catalyst surface. So we would not know what's the value, right? We only knew the value of concentration of N, not the concentration of N at the catalyst side. So we need to substitute this value Cn dot S and also Ci dot S. How are we going to do that? So that's why we need these two which is Ra and also Rd to determine our CNS and also CIS. Okay, so when the surface reaction is the slowest step, adsorption and also desorption, we can assume it as a rapid step. Okay, we already neglect the diffusion step because it's rapid. Okay, in the first place we already neglect the diffusion. Okay, but at this step since we choose surface direction as the slowest step, so opposite of the slowest step is a faster step. So adsorption and desorption would be the fast step. Okay, so a fast step will have a reaction rate and reaction rate high, right? So when RA is high, so okay, here where I explain. So from RA is high over KA, which is also high. So this value will nearly to 0. Same goes by RD over KD. It will be near to 0. So from the equation earlier, so when this value is equals to 0, then you can make PNCV is equals to Cn dot S over Kn, like in the next slide. Understand? So similar goes by the CV. So this is step 3, where you need to determine the N dot S, so CIS, and also concentration I dot S, so that you can solve this final reaction rate. Right. Okay. However, although we have determine what is Cn dot S and Ci dot S, so it's equals to this term and also this term. Still, we don't know what is CV. We cannot measure what is CV. CV is a vacant site in a catalyst. We cannot see. We cannot know. Okay. So we need to change it into a more meaningful terms. Okay. So that's why, okay, we have this site balance. Okay, so CT is concentration of active site. This is what we know, okay, from the from the data given to us when we purchase a catalyst, right? And then it's equals to CV plus Cn dot S plus Ci. This one is what I have described earlier in the previous slide, in the previous part. Okay, so you substitute this equation Cn dot S, Ci dot S, and also you into this CT, and finally into this RS. So in the end, you will see that this is the final, the final overall rate of reaction for this reaction. Okay, for reaction of N-pentene producing I-pentene. If you look later on, you will see that, okay, right, okay, right, okay, so we can have, okay, never mind, let's say I'm trying to draw something here. Okay, all right, so this will be the final part of your rate law, but you can still simplify it. Okay, so normally what they do will be, this part would be, okay, this part, okay, I think it should be here. Okay, sorry, again here. Okay, this part will remain, when you simplify it will become K. All right, so in some example, okay, so it will be simplified into negative Rn is equals to Kpn minus Pi over K, this is P, right? So like in your textbook, okay, so it's just similar. If you go through for some example here, okay, since there's a rate law mechanism, okay, you can try and do it by your own, okay, especially that involve the LE radial. So I think maybe in the next part of this chapter, I will explain the reaction with LE radial mechanism. Okay, all right, till then, thank you. See you in the next part later.